Lesson 59, free body diagrams. We'll be able to construct free body diagrams. Mute myself for a second while the garbage truck. Okay, so free body diagrams, we're going to explain what those mean in a little bit of time, but what we want to do first is I want to finish up the conversations that we were having about some of the fundamental forces. Not fundamental forces, some of the forces that we're going to be discussing. The first force, let's go backwards a couple of slides. So the first force that we talked about was, we said a force is just a push or pull. It's measured in newtons. It has direction and size because it's a vector. We said that there are a difference between contact and non-contact forces. Contact forces means it has to be touching something, whereas a non-contact force can act without touching something. And we've sort of said that a force can cause something to move or change shape. So if you, if you're applying a contact force, if you're pulling on something like a string, then yeah, you're changing the shape of it. You're stretching that string out. We talked about the very first one, which was gravity. We said that gravity is a non-contact force, and we said it's mostly the Earth that is pulling things towards it. Everything moves towards the Earth. The bigger you are, the greater the force is towards the Earth because you have more mass. But you can break the force of gravity. What's holding the Earth in place? Well, the thing holding the Earth in place is, of course, the sun. Everything is attracted to the sun. And that's, yeah, again, it's the same sort of thing. It's like for the Earth, the sun is there. Us standing on the Earth, we get pulled towards the Earth. The Earth gets pulled towards the sun. The sun gets pulled towards the center of the Milky Way, and so on and so forth. We talked about the difference between weight and mass, and then after I finished explaining the difference between weight and mass, I said, guess what? We're never going to use this. We're never going to use the word weight again. But it does give us a quick definition here. We've got F equals mg. The force of gravity is given by the mass times the gravitational potential, which is 9.8. I will point out that this changes depending on where you are on the Earth. If you're at the top of a high mountain, it might differ to if you're at the, it differs. I think it's like if you're near the North Pole, it's less than if you're near the equator because the equator has more mass under it. If you're at the top of a mountain, it can be a bit of A or B. Because you're very high up, it's a little bit less force. Because you're on top of a mountain, which has got a large amount of mass, it can mean more force. If you're in a plane, you'll feel less gravitational force. But of course, these things are all like, it's when I say a little bit less, I'm not talking about, oh, when you're, at the North Pole, you'll be weightless. It's like, no, it's like 9.81 versus 9.82 or whatever. We talked about frictional force. I added this symbol here, so FFR. So that's usually how I write the frictional force. It's created when two surfaces come in contact. It only slows or stops an object from moving. Air resistance is the same as the frictional force, except it works with the air. And we talked about, well, what causes the frictional force. Two surfaces are rough, so they don't slide. Heavy objects push together and have more friction. So the lighter objects, heavy objects push surfaces together and have more friction than lighter objects. Try moving a bookcase. So it's a bookcase or a book, like, it's really heavy, so it's hard to move along the ground because it's pushing these surfaces together, and that makes it a bit harder for you to move. There are some ways you can reduce friction, so reduce the amount of force that's pushing between these two things. This is a slide, as I said, some of these slides have come straight from year 7. I could have got rid of this slide, but I thought, you know what, nah, my year 11 students can just look at this slide really quickly. How can you reduce friction? Because the idea that I want to show you guys here is that not necessarily about memorizing this, but just how to think about it. If friction is caused when two surfaces are, when two surfaces are pushed together and they can't slide past each other easily, how can we reduce that friction? There's a couple of ways. You could use balls or wheels or rollers, and they have less surface area touching. So wheels are great for reducing friction. If you look at a wheel, right, a wheel is going to be, watch this circle. Yeah, okay, it's a great circle there. A wheel's only got a small part of surface that's actually touching. Okay, so therefore, because it's got such a small area of surface touching, it reduces the friction. It's like, you know, it's like one of the classic ones that I've heard is that in a wheel of a car, even though the wheel of the car is so big, only about a hand span's worth of space is actually touching the road at any time. So therefore, even though you've got your car and it's got all the weight in the car and all the engine and everything that's all pushing there and creating friction, ultimately it's just a small hand's worth of surface that's touching it. So therefore, it's hard to build up a lot of friction. Lubricant or polishing the surface. So if we want to make if we make the surface smoother, then it's going to reduce the amount of friction. Remember, friction is caused by the roughness. The rougher the surface, the less, the more friction there is. So if you can make it smoother, then yeah, that's better. What if you took this first idea, and this third idea is like taking this first idea and taking it to the extreme. What if you take this first idea of making less surface and you took it to the level where you put no surface between them? You put air between them. So you separate the surfaces. So yeah, that means there can't be any real friction at all. That's how we get maglev trains. That's how we get hovercrafts. All of these things push air between the surfaces, and sometimes even some doors have a little bit of air being pushed along the bottom to try and make them slide easier, because you want to push those surfaces apart. So you could, of course, push them. This is all of these are sort of the same in that all the top three are all about making the surface, lowering the surface pressure. This one again lowers the surface pressure, but it does it in a different way. You make less mass. Less mass means it's lighter, means you push down less, so there's less friction. And yeah, these are 4 ways that you can decrease the amount of friction. Do you need to know these? Not necessarily. But what's important, I think, about this slide is not necessarily that you need to study, but you need to be able to problem solve and think, oh yeah, okay, so if friction is caused by 2 surfaces touching each other, how can I reduce the amount of touching that goes on? And here are just a couple of ways that you can do that. So there might be other questions you'll see, and it's like, oh, the tension force, how can you reduce the tension? How can you increase the tension force? So on and so forth. Is friction always a bad thing? Well, friction can be good, and friction can be bad. Friction can be bad if you friction can be bad if you want to try and move something quickly or move something heavy. Friction's the worst. If you've ever tried to move house and you're trying to carry a bookcase, which believe me, I've done recently, it's not pleasant because it's so heavy and it's got a lot of friction. So if you can reduce that friction, it makes your life easier. So, but is friction always bad? No, not necessarily. Friction can be good. If you want to make something warm, friction's great. If you want to stop something, yeah, guess what? You need to have friction. So yeah, friction really important when you want to stop a car from moving or slow down because you've got air resistance. Or even on the bottom of your shoes. If you didn't have friction on our shoes, we'd be sliding around everywhere. And of course, friction can be used to create heat in your hands. And then of course, also to create like sparks if you try and light a match. So friction's not always a bad thing. But yeah, that's enough talk about friction. Let's talk about 2 more forces. The next force I wanted to talk to you guys about is the normal force. And again, by the way, I say to you guys again, if I'm going too quickly, please let me know in chat because I'm just going to go this pace. I have been starting to upload some of these videos onto YouTube, but it's a bit of a slow process. So I'm not punching these things out, I'm not like a content creator. I'm not pushing these things out daily. It's not my full-time job. So yeah, frictional force. When you push on an object like a chair, the object pushes back. Now, most of you guys will know that that's like a bit of a hint towards Newton's third law, but we're not talking about Newton's laws yet. We're just going to keep it nice and basic. This is a reaction force. If you push down on the chair because you're sitting on the chair's going to push up on you. And this reaction force is known as a normal force. For those of you that end up doing mathematics, a normal means that it's perpendicular to a surface. So if you notice here, the surface of the chair is here. The normal force is acting perpendicular to that. And normals are always perpendicular to the surface. It is actually caused by the electrons in both objects repelling one another. So the objects in the person's butt is being repelled by the electrons in the chair. And that's why these things you don't just pass through a chair. You can't just walk through walls because the electrons are pushing against you. Interestingly, in the book, they relate this back to the frictional force. The frictional force is also due to the electrons repelling each other, but it happens parallel to the surface. So therefore, even though I keep saying, oh, it's rubbing is going to cause friction, even if you've got two surfaces that are really, really smooth, and they slide past each other, there still will be a little bit of friction because the electrons in one will repel the electrons in the other. It just happens to be the rougher the surface, the more contact there is, and so therefore the more friction you'll get. So that's the normal force. We're actually going to use the normal force a lot to sort of explain, to deal with our force diagrams. But yeah, the normal force is quite simply just a reaction force to something happening. Let's talk now about the last two forces. What time have I got here? Well, I've wasted 25 minutes. That's all right. We've got a little bit of time left. We should be able to make it. The first of the extra types of forces, and I actually don't usually talk about these forces in any of my subjects, engineering or year 10, and I don't think it gets taught in year 10 advanced maths, but these are the extra two forces that get talked about briefly, but we're going to spend a little bit more time on them today. The first is called a compression force. Now, a compression force is a force that acts when two objects are being pushed towards each other. This picture was taken straight out of the textbook. It's got a big house that happens to be sitting on a concrete pillar. Pretty sure it's a concrete pillar. And you've got the heavy house. It's going to push down on the pillar. Okay, so this is the force on the pillar by the house. You're also going to have the force on the pillar by the rock, because the rock's going to push back up. And that's going to create a compression force. Now that compression force is going to squash that pillar. Now it just so happens that stone and cement really don't like to be squashed. They really are against it. So therefore, the compression force is actually a really strong. It's a really good way to create a force. It's just essentially, it's also, by the way, we can tell that if we always just break things down into push and pull forces, the compression force is a push force. This is also why there's a lot of analysis in when you look at structures as well. This is why bridges are built the way that they are. So bridges, when they're built like this, the reason that they're built like this is because you can have a lot of compression, push down on things. That's why, of course, the pyramids have lasted for so long, because they are stone that's all being squashed. And stone that's being squashed is really, easy to deal with. Whereas, you would never be able to build a pyramid upside down, because that would require a lot of the next type of force. The next type of force is the tension force. I'm going to change the slide unless someone says, no, please don't. I did miss out on these forces up here. There are some extra forces in here to balance out these forces. Even though the ground is pushing up on the pole is still pushing down the ground. All of these forces are ultimately balanced. We're not going to discuss how they're all balanced today, but I'm going to just tell you that they are. Because when we talk more about, which is next week probably, or maybe even Friday, when we start to go through Newton's laws, we're going to have to deal with balancing forces. So the tension force. Now the tension force is the cousin of the compression force. It's the opposite. If you notice, all I did was change one word here. This is the force that acts when the objects are being pulled away from each other. So instead of squashing something, now you're pulling it, you're stretching something. Now, when it comes to stone and concrete and cement and bricks, they are really bad at tension. That's why, as I said, you'll never, like, you couldn't build a bridge out of just concrete. Because if you built a bridge out of just concrete and you just had like one pillar here and then a big slab of concrete. When I talk about a big slab of concrete, I'm talking about, you know, a kilometer of concrete, because there would be stretching happening here. As this gets pulled down, it would stretch the concrete, it will fall apart. That's why you have to put metal inside the concrete to make sure it doesn't fall apart. Metals are a good material to withstand tension. If you have a look at this picture here, I would start from this picture at the bottom here. We know that this heavy mass here is going to get pulled down by gravity. Now, if it's getting pulled down by gravity, it's going to pull on this wire, right? And if it pulls on the wire, it's going to create a force. So you're going to have a force on the, so the crane's going to be pulled down by the cable, but the cable is going to be pulled up by the crane. And the other direction is the force of the cable on the mass. So I actually don't fully get how they've done all these forces. I feel like Earth on mass, I feel like some of these forces are in the wrong direction, but the ultimate thing that I want you to understand, this cable here is under tension. It is being pulled from both directions. It's getting pulled down by the mass, and then that makes the cable is then being pulled on the top. So the top of the crane isn't moving downwards, so it's pulling up on it. So it's getting pulled in both directions. So those are the main forces that we're going to be using to study motion. Gravity, friction, the normal force, tension and compression. We're going to be using those a lot when we discuss these types of this type of motion. Then now we're going to talk about, what time have we got? 11:30. We're now going to talk briefly about force diagrams. Now, many of you guys have seen these before, but I still want to go through them anyway. We're going to start with this. So first up, what we've got is we've got a force diagram, which is we just got two apples floating in space. Okay, one of these apples happens to be moving through space. The other apple happens to be just, you know, sitting in space doing nothing. Now, there is no force acting on either of these apples. You might be saying, but this apple here is moving. Doesn't matter. Just because it's moving doesn't mean that there is a force acting on that apple. So therefore, there is no forces acting on this apple, on these apples whatsoever. The reason I can say for certain that there are no forces is because they're not accelerating, but I'm not going to go into that because that's Newton's second law that we haven't taught you guys yet. But I can see that there's no suns have gravity, there's no pulling or pushing forces, it's just an apple sitting in the middle of space. So if that's the case, then what happens when we start to introduce forces? How is that going to work out? Well, let's bring in let's put our apple on the earth. Okay, so now we've got an apple on the earth. Now, here's a question for chat. Let's see if you guys are actually participating in the lesson or whether you're just, got your screens logged into Zoom and you're not actually doing something. Can you guys tell me, are there any forces? This apple is sitting here on the ground. It's not moving. Are there any forces acting on this apple? Gravity. Yes, thank you. Oh, yeah, look at that. There is gravity. There is also a normal force. Yep. Beautiful. So, this is the most participation I've actually seen in a long time from like a class. The amount of like engineering math classes I've had where people are going to just don't say anything. So we've got one force downwards. I'm actually going to draw this force in with the arrow going down. I'm going to write Fg. That's for gravity. Now that force is being pulled downwards. It's got a note, so this is a vector because it's got a direction and a size. So that is getting pulled downwards, but it's also getting pushed upwards. Okay, and it's getting pushed upwards by, in this case, as we said, the normal force. The normal force is going to push. Oh, God, okay. Let me just try that again. That was actually kind of bad. There we go. Let's see if I can get a straight line going up. If not, I'm just going to give up. Come on, straight line. Well, that's better. So that force upwards is going to be the normal force. Now, it just so happens that for this apple, that the normal force and the gravitational force are the same. So what we would do for that is we would say F net. So the overall force is 0. You can say, if you want to do, you can say F net, or you can also say, if you don't like to do F net, which I'm like, I don't know why you would want this, you can use a symbol. And so this symbol here, which looks like I'm just trying to do a fancy E, means the sum of all the forces. If you add all the forces together, then they equal 0. I prefer F net because it's like the net force for this overall force. But yeah, if you add these two forces together, they're 0. I can tell you why it's 0 is because it's not moving. Its velocity is not changing. It is just staying where it is. So therefore, we know that all of these forces are balanced. When you have a 0 force, that means that your forces are balanced. I so miss my board so much, but yeah, balanced. Let's take a different example. Let's take our apple, and what we'll do is we'll replace it with a bookcase. But what we're going to do with this bookcase is we're going to, whoopsies. What we're going to do with this bookcase is we're going to move the bookcase. Okay, so if we try and move this bookcase, we're going to have the same forces that we had before. We've got a force downwards, which is going to be gravitational. We've got a force upwards, which is going to be the normal force. Now, if we are standing against this, if we're standing against this bookcase and we're trying to move it, what we want to do is, if we're pushing against this bookcase, we're going to be pushing to the right. So I'm just going to draw an arrow here and I'm going to write F. Now, here's the question. This is a really heavy bookcase. Are there any other forces that I have forgotten on this picture here? Have I got all of them, or am I missing any of them? What do you guys think? Friction. Yes, we are missing friction. There is going to be a frictional force because obviously it's a bookcase. It's not on wheels. There's going to be a little bit of friction here. And the friction is going to be on going the opposite direction, going to the left. Okay, so what we could do is, you know, we could talk about the net force. We could say the net force vertically. So we could say the net force vertically. Well, that's, yeah. The net force vertically, we could say that's equal to 0. We could say the F force, the F net horizontal, well, that's going to be equal to the force, the push force, minus the frictional force. And I'm keeping this a bit general here because we could say, let's just say that our frictional force and if our frictional force and our push force are the same, then the net force is going to be 0. Obviously, our frictional forces could be more than our could our forward force, our pushing force could exceed the frictional force, and then we could maybe start moving that bookcase. But or our frictional force could equal our push force, and we could actually have some movement happening there at a constant velocity. But yeah, if the frictional force is bigger than the push force, then there's going to be no movement. Now you might think to yourself, but if the frictional force is bigger than the push force, you'll have a negative force. So then the bookcase will fall backwards, but it's not. That's not how friction works. Friction does not make something move. Friction only ever slows something down. So the frictional force will not be, the frictional force is more, will only ever equal or be less than the push force. But yeah, I'm just trying to get you guys to see, oh, you know, we're talking about these forces. Now we can start to actually, like, you know, get them into pictures. Let's do, I think we've got this one here. We've got a woman that's riding her bike again. Do I want to do this? What time have I got? Let's move. I'm going to move on from this one. But yeah, for the girl riding a bike, it's the same idea as the bookcase. The only difference is that she's moving at a constant speed. Even though she's moving at a constant speed, it doesn't mean that her forces are her forces aren't balanced. Her forces are all balanced because she's moving at a constant speed. That's something that I haven't talked to you guys about yet, but I will now. If your forces are balanced, that means you are not getting faster or slower. The last thing, I guess, would be the apple falling. If you've got an apple falling, there's only one force acting on this apple. Okay, that's a lie. There's two forces, but I'm just going to do this. That's the gravitational force pulling that down. Now, some of you guys who are smart asses will say, yeah, but so what about air resistance? So I would say, yes, there is technically air resistance going up. But usually what we'll do in questions is we're going to ignore air resistance. That's actually going to be the situation most of the time. Air resistance will get ignored. But yeah, I just wanted to just throw that out there just to say, hey, yes, you can have, this is an unbalanced force. F net, in this case, equals F of G. Even if you did want to be a nerd and add the air resistance, all that would do is you'd end up with F net equals F of G minus the air resistance force. And that air resistance force is probably not going to be, again, it's like friction. It can be equal to or less than the friction in the gravitational force. But yeah, it's just going to be that's just when you have the case of an unbalanced force. So these are all what we would call force diagrams. But to be honest with you guys, in physics, we don't usually draw force diagrams with respect to, we don't usually draw fancy shapes like apples. What we usually do is, because we're lazy, all we do is single points. So in this example here, I've got a single point sitting here. I've got a force upwards of 4 newtons. I've got a force downwards of 6 newtons. And this is how I would draw it, as I just draw a point, an arrow going up and an arrow going down. To be honest with you guys, I would actually just do this, but because, yeah, and yeah, I would just do that. And there we go. Now that point here, that object could be a bookcase, it could be a person, it could be a yo-yo, it could be a baby, it could be anything. What we do is we use a point to represent the center of mass. Now the center of mass is a concept that is, we just sort of assume in year 11 and 12 physics that all force comes from a single point. It all acts on a single point. When you get to the university physics, that's when they start to say, all right, we're going to start looking at these forces as acting on objects of how is it going to be different if you acted on a cylinder. And that's when I started to fail physics, and that's when I stopped doing physics, because I'm like, oh, this got really hard. But the basics is, yeah. Can someone tell me what's the net force on this yellow arrows here? What's the net force? What's the net force on this one here? Remember, force is a vector quantity. Come on, 2 newtons down. Thank you for clear. 2. Kelvin, caught you. You said 2. You did not say 2 down. 2 newtons down. Remember, you must have a direction. So if you just wrote down 2, then they would be wrong. How did you get 2? Well, we had 4 going up and 6 going down. You could work that out by saying, well, let's take up to be positive. We've got positive 4 going up plus negative 6 going down. And that's how we get to negative 2. And for more complicated ones, you probably want to do something like that. Let's do this next one. I haven't pushed these arrows close together. Sorry about that. But hopefully, you guys, that was just because I was lazy here. Can you guys tell me what's the net force for the green one? You're right, Kang. It is 0 newtons. Now, because the magnitude is 0, I don't need to give a direction because, it's not going anywhere. So there we go. The reason we got 0 is, again, we've got plus 6 minus 6 is going to be 0. What about when we do something like this guy here? What's the net force for this blue one? Let me just change. 10 newtons to the left. It so happens that in this example over here, we end up with is, well, lost my thing, is that this 3 newtons is going to cancel out with this 3 newtons. So we just end up with F net equals 10 newtons to the left. That's actually the best writing I've done so far. 10 newtons to the left. So that's that one there, and that's because these two balance. What about one more easy? This one here, this red one. How is this red one going to work? This would be so much easier if I was doing it. 2 newtons to the right, 2 newtons to the right. Brendan's getting the hang of it. Cool. So this 4 and this 4, they cancel, and then we've got 8 and 10. So therefore, that's going to be, 10 minus 8 is going to be 2. We've got F net equals 2 newtons to the right. And then our last example, which is going to be the last 3 minutes, and I'm not going to have enough time to do this properly, but I'm going to throw it up anyway. This is the type of stuff that you guys are going to be seeing a lot more often. You have 4 newtons going up and 5 newtons going to the right. Now, if you wanted to calculate the net force here, it is not going to be as simple as just, it's not going to be as simple as just going, oh, 4 plus 5 is 9 newtons. That's not going to be the case. What you're going to have to do is you're going to have to say, well, it's the same as having a force going to the right of 5 and a force going up of 4. So therefore, this line here is the line that we want to be calculating. That's the force that we're going to calculate. I'm going to do this question in the last 2 minutes that I've got with you guys. But if you guys need to leave right now, you can. But I'm going to try my best to do this in the last 2 minutes. So if you want to stay, if you want to just stay for a little bit, I'm going to push through it as quickly as I can. Okay, here we go. Here we go. Rapid fire. We've got, let me make sure, we've got a point. We've got 4 newtons going up. We've got 5 newtons going to the right. That is the same as saying 5, 4 with a line going up like this. Okay, so therefore, if I want to calculate the length of that line, I'm going to have to use my vector quantities. I'm going to have to go, well, that vector quantity there, the force, the size of that force is going to be the square root of the vertical force squared plus the horizontal force squared. That's going to have to be 4 squared plus 5 squared, which is going to be 40. Let's do this in the calculator. Square root of 4 squared plus 5 squared, 6.4. Great, cool. What about the direction? Okay, well, the direction. To work out the direction, we're going to go inverse tan. This is why I showed you guys how to do this at the very, very start. Inverse tan of opposite over adjacent, which is going to be the inverse tan of 4 over 5, which is going to be, whoopsies. Inverse tan of 4 divided by 5 gives us 39 degrees. Okay, let's go with that. So the force, the net force is equal to 6.4 newtons at 39 degrees, and you can leave it like that. If you want to be if you want to be precious, you can say at 39 degrees from horizontal. If you want to be 100% sure that your examiner is going to give you a correct mark, but that's how you would do it. And you guys are going to see a lot more of these types of things than you will probably see of the easy ones that I gave you. But the idea is that you can still use your logic to get to that. If I give you one that looks like this, I've got to stop now because you guys are 10, 12, 14, 16, then that's going to break down into vectors that look like this. 2 down and, oopsies, 2 to the right. So then you can use that to find out, well, you know, and so on and so forth. And figure out, well, what's that vector going to be? What's the angle all the way around here going to be? Blah, blah, blah. I'm not going to do that, but you guys can figure that out. Right, that's the end of this lesson. Probably on Friday, I'm going to give you guys the majority of the lesson to, I'll probably do a little bit more of this stuff, but I'm probably going to give you guys the majority of the lesson to work on 10.2 to get that under our belt. I do want to go through this in a bit more detail though, so be ready for that. Otherwise, guys, I will see you guys Friday. Take care.